Okay, hello. Okay, this would be the second part of the concept of linear programming. So this is all about the graphical method of solving linear programming model. So if you have already watched the part one of about linear programming, so in the part one, we have discussed there about how to create an LP model. So we have to determine the objective function, the constraints, and the non-negativity constraints. Now here on the second part, we are focusing on using the LP model, so the one that we have created, to determine the optimal solution. And in the mathematics in the modern world, uh, we use the concept of graphical method. So these are the steps of the linear programming problem. So for number one, we need to formulate the linear programming model. So again, you cannot find the optimal solution of an LP problem if there is no LP model. So for those that have already watched the part one, so this is the continuation, no? But for those that starts with this part two, so I recommend that you should see the part one of this video. So for number two, you need to graph the feasible region and find the corner points. And the coordinates of the corner points can be obtained by either inspection or by solving the two equations of the lines intersecting at the point. So since you already have your LP model, we are going to use the constraints of the model to graph in a coordinate plane, and we need to find the corner points. So usually the coordinates of the corner points are either in the intersection of the two lines, as long as we need to take note that all of the values should be in the first quadrant, since we assume that in the non-negativity constraints, both all of our decision variables should be greater than or equal to 0. Number three, we need to make a table listing the value of the objective function at each corner point. So as you have already identified all of the corner points, now we are going to substitute all of the values um, of these points in the objective function by creating a table. And for number four, we need to determine the optimal solution from the table in step three. Now, if the problem is of maximization, so take note, in maximization, we need to find the largest value of the objective function. But if our problem is all about minimization, we need to determine the solution that will correspond to the smallest value of the objective function. So we have this fundamental theorem of linear programming. It says that if the optimal value of the objective function in a linear programming problem exists, then that value must occur at one or more of the corner points of the feasible region. So in the graphical method, it's important that we identify the corner points, because in the corner points, um, the value that we are looking for, either it's the maximization or minimization problem, then on the corner points, that is where the optimal solution is found. So that's why it's important that we have to locate the feasible region, and specifically the corner points. So let's have this example one to illustrate the the theorem, and as well as how to do the steps in linear programming model. So let's have this example. A furniture company produces inexpensive tables and chairs. The production process for each is similar in that both require a certain number of hours of carpentry work and a certain number of labor hours in the painting department. Each table takes 4 hours of carpentry and 3 hours in the painting department. Each chair requires 2 hours of carpentry and 1 hour in the painting department. So during the current production period, 240 hours of carpentry time are available and 100 hours in painting is available. Each table sold yields a profit of 7 pesos. each share produced is sold for a 5 peso profit. Find the best combination of tables and shares to manufacture in order to reach the maximum profit. So which means to say that our problem is all about maximization. So we begin by summarizing the information needed to solve the problem in the form of a table. So remember, it's important that you should know the resource availability, because in the resource availability, that will determine our constraints. And we could also make a table, to easy identify. Um, for example, in this problem, it's easy for us to create the LP model if we have this table. So if you recall, in the department, we have two. We have the carpentry and we have the painting. So we have two products, and that is all about the tables and shares. So according to the problem, uh, for tables, to create 1 unit of table, it requires 4 hours of carpentry. And to produce 1 unit of chair, it requires 3 hours of carpentry. And remember, according to the problem, we have 240 available hours. For in the painting department, to paint one table, it requires 2 hours of uh, 2 hours of labor, no? And for to paint one chair, it requires 1 hour, no? 1 hour per unit. And the available hours is 100. So if we solve the table for every 1 unit, it will cost 7 pesos. And for the chair, to solve it at 1 unit, okay, the profit will be 5 pesos. So with this, we have now the model components. So let's go to the decision variables. So of course, our x sub 1 would be the number of tables to be produced. And for x sub 2, that's the number of chairs to be produced. So our objective function is to maximize. Say we let z as our profit, then our function would be 7x sub 1 plus 5x sub 2. So remember that 7x sub 1 means to say that for the number of tables, every table is sold at 7 pesos. And for the number of chairs, every chair is sold for 5 pesos. So that's why we have that objective function. For our resource constraints, we have 4x sub 1 plus 3x sub 2 is less than or equal to 240. So remember that in the table, for every one table, it requires 4 hours of carpentry. And for 1 unit of chair, it requires 3 hours of carpentry. So that's why we have 4x sub 1 plus 3x sub 2 is less than or equal to 240. Now we use less than or equal to because we know that 240 is the maximum number of hours of carpentry. And we have also this constraint 2x sub 1 plus x sub 2 is less than or equal to 100. So this is for the painting, no? The number of hours in the painting department. So for the table, it requires 2 hours of painting, and for the chair, it would require 1 hour of painting. So this would be now our constraints, and do not forget our non-negativity constraints, which is x sub 1, which is greater than or equal to 0, and x sub 2 greater than or equal to 0. So always remember that we have to assume that all of our decision variables are all positive, or 0 and positive, no? Since we are talking here about profit. So after creating now the model components, so we are now on the second step. So which is to graph, to graph. And again, when graphing equations, linear equations specifically, so to find the optimal solution to this LP using graphical method, so first we need to identify the region of feasible solutions and the corner points of the feasible region. but we cannot graph, uh, we cannot just simply automatically graph using the given resource constraints. And what we are going to do is we need to solve for uh, the intercepts of each of these linear inequalities. So again, we use the constraints. So when we solve for the intercepts of these inequalities, it's just the same with how we graph linear equations. So what we do is we assume, or we let this equation be a linear equation by instead of using this symbol, we equate this. So instead of using this, we use the equal sign. So that we would be able to get the intercepts, no? So for this first intercept, we have 4x sub 1 plus 3x sub 2 is less than or equal to 240. So recall in intercepts. So in intercepts, okay, the first thing that we do is we let x sub 1 be equal to 0. So that's the rule, no? And then we solve for the x sub 2. So we substitute 4 times 0 plus 3x sub 2 equals 240. So this is 0. So what remains is 3x sub 2, which is equal to 240. And then we divide both sides by 3, or we can multiply these by 1/3. So to eliminate the coefficient 3. So it becomes x sub 2 equals 80. So meaning when x sub 1 is 0, our x sub 2 is 80. And then after letting x sub 1 be equal to 0, we now let x sub 2 be equal to 0, and then we solve for x sub 1. So by substituting, 4x sub 1 plus 3 times 0 equals to 40. So 4x sub 1, this is already 0, so which is equal to 240. And then we multiply both sides by 1/4. So we have x sub 1 equals 60. So when x sub 1 is 60, your x sub 2 now is 0. So that's why we have now these intercepts. Now we also have the second constraint, which is 2x sub 1 plus x sub 2, which is less than or equal to 100. So the same process, we let x sub 1 be equal to 0, and we solve for x sub 2. So we have 2 times 0 plus x sub 2 equals 100. So this is 0, and this is x sub 2 equals 100. So which means to say that when x sub 1 is 0, our x sub 2 is 100. And then we let x sub 2 be equal to 0, and we solve for x sub 1. So 2x sub 1 plus 0 equals 100, or 2x sub 1 equals 100. And then we multiply both sides by 1/2. So when multiplying 1/2, it would give us x sub 1 equals 50, which means that when your x sub 1 is 50, your x sub 2 now is 0. So we already have the intercepts of the two constraints. Aside from that, we need also to find the intersection of these equations. So meaning what we do is we simultaneously solve this system of linear equations. So again, these are the constraints, okay? So we just simply replace the inequality symbol. So if you recall, the inequality symbol is less than or equal to, but we just simply change that to equal sign so that we would be able to get uh, the, the point of intersection of these two lines. So again, in solving systems of linear equations, there are a lot of methods. You could use the substitution method, the elimination method, or you could have the transitive property of equality. So it's up to you whether what's your to any of these methods you can use to solve the point of intersection. But for the sake of this video, we use the concept of substitution. So here what we do is from the second equation, we solve for the x sub 2. So by subtracting both sides by 2x sub 1, so that's why it becomes, so from this, we have this, no? X sub 2 equals 100 minus 2x sub 1. And then what we do is this equation 3 is substituted to the first equation. So that's why we have here 4x sub 1 plus 3 times the quantity of the x sub 2 now is replaced by 100 minus 2x sub 1, which is equal to 240. So this is 4x sub 1 plus 3 times 100, that's 300. And 3 times negative 2x sub 1, that's negative 6x sub 1 equals 240. So adding similar terms, so 4x sub 1 minus 6x sub 1 would give us negative 2x sub 1 plus 300 equals 240. And then subtracting both sides by 300, so we have negative 2x sub 1 equals negative 60. And we divide both sides by negative 2, which would give us x sub 1 equals 30. So to solve for x sub 2, we could use the equation 3 by substituting x sub 1 as 30. So we have x sub 2 equals 100 minus 2x sub 1. Then we substitute x sub 1 as 30. So x sub 2 equals 100 minus 2 times 30. Or we have x sub 2 equals 40. So meaning the point of intersection of the two lines is 30, 40. So we can use these points to plot and determine the feasible region. So we have here, so for the first constraint, that's 4x sub 1 plus 3x sub 2 is less than or equal to 240. So this blue line. So recall that our points of the intercepts of these equation is we have 0, 80, and we have 60, 0. And then we are going to make this shade, okay, because we know that the relation symbol is less than or equal to. And then for the second constraint, we have 2x sub 1 plus x sub 2 is less than or equal to 100. So upon our computation, we found out that the intercepts are 0, 100, and 50, 0. So we are also going to shade going to the left because we know that the relation symbol is less than. So that is how we graph linear inequalities. Okay, now what we're going to do is you just simply need to identify the feasible region, or that is the area of the two lines where the solution is found. So basically that's the intersection of the graph of the two equations. And we found out that you also have to take note also that because of the non-negativity constraints, we only restrict all of our values to the positive area. So which means that we are only concerned with the region that has the positive value. So if you try to look at the area, which is the intersection of the solution of the two lines, is on this portion. Okay, that is the area where the solution of the two lines meet. And we restrict this area. So take note, we have this green portion because we have the non-negativity constraints, which is x sub 1, which is greater than or equal to 0, as well as x sub 2 greater than or equal to 0. So meaning to say, this is now what we call the feasible region, or the common solution to both of the two lines. Now with this, we are now going to identify the corner points. So the corner points are 0, 80. Okay, this point of intersection, the one that we have solved, the 30, 40. So if you recall, this is the point of intersection of the two lines, as well as this point, which is 50, 0. And we also have the 0, 0. So these are the corner points. And then what we're going to do is in step 3, we are going to list and create a table. So we have already these corner points, 0, 0, 0, 80, 30, 40, and 50, 0. Then what we do is using our objective function, which is 7x sub 1 plus 5x sub 2, we substitute the value of the corner points to the objective function. So for example, if you have 0, 0, that's 7 times 0 plus 5 times 0 would give us 0. So take note that Z represents profit. For 080, we have Z equals 7 times 0 plus 5 times 80, and that would give us a profit of 400 pesos. For 3040, Z equals 7 times 30 plus 5 times 40, that would give us 410 pesos. And for 50, Z equals 7 times 50 plus 5 times 0 equals 350 pesos. So since the problem is maximization, and since the largest profit is 410 pesos, we can say that 3040 is the optimal solution. So this is now our optimal solution. So because the point 3040 produces the highest profit, we conclude that 30 tables are produced and 40 chairs will yield a maximum profit of 410 pesos. So to get the number of chairs and tables produced, which means that table is 30 pieces. So we have 30 pieces for the tables, and x sub 2 is 40 pieces for the number of tables. And the maximum profit of that would be 410 pesos. So that is for graphical method of linear programming. So actually there are a lot of methods of how we get the optimal solution, but for mathematics in the modern world, okay, we use the concept of graphical method to get the optimal solution of a given linear programming model. Okay, you can also try this at home. So construct an LP model for this given problem and solve it using the graphical method. So I hope that you have learned something from this second part. Thank you for listening.